In last two models already covered, we cleared this model. These two models, the third model is discovered by these scientists, Ernest Rutherford, and model name is nuclear model. In the year 1911, he discovered this model. What he theorized that atoms are mainly empty space. The main positive charge is concentrated at the center of the atom, and it is called as nucleus. And surrounding this nucleus, the center of atom is nucleus, and surrounding this nucleus, the electrons are moved. So to clear your idea, I will show you one small video which will clear you this idea.
Rutherford's gold foil experiment gave him interesting results. What results did he get, by the way? Let me recall them for you. He found that most of the fast-moving alpha particles passed straight through the foil and hit the detector. However, some particles got deflected by small angles. And lastly, to his astonishment, few alpha particles also rebounded. Now, how can this be possible? These three observations made Rutherford think that the plum pudding model is not really correct. Let us take a simplified example to understand the inferences first. Let us imagine that we have a ball made up of cotton. The cotton in the ball is very sparsely distributed and has an extremely tiny circle or sphere located at the center. This sphere is quite hard and dense. So hard that it can even resist a bullet shot against it. Now what will happen if you shoot many bullets across this cotton ball? Most of them will travel straight through the cotton surface. What will happen if a bullet hits the edge of the central heavy mass? In this case, the bullet will slightly change their path and get deviated. So looking at the size of the central mass, it's obvious that only some of the bullets will get deviated. Lastly, what happens when a bullet hits the center directly? Needless to say, it will bounce back, because we know that the central dense mass is too hard for the bullet to pass through. So very few bullets will bounce back. This is analogous to what Rutherford had inferred about the atomic structure. His first conclusion was that most of the space inside an atom is empty. This is because most of the alpha particles could easily pass through the atoms and hit the detector straight. Now, if most of the space is empty inside an atom, then where is the positive charge located? Well, that's the second conclusion. The positive charge is compactly packed in a tiny entity. This occupies an extremely small space inside the atom. Now, why did he think so? Let's go back to our cotton ball and bullet example. Can you recall the second and the third case? Yes, the bullets get deviated on hitting the tiny sphere of the edge, and they will rebound when they hit the center. Same explanation holds true for this. A few alpha particles get deviated. That means there is a possibility that these hit the edge of the positive center. Yes, and one more possibility is that they get deviated because the positive center repels the alpha particles as they're also positively charged. Also, a very small number of alpha particles rebounded. That means there is a possibility that these alpha particles had directly hit the positive center. But since the number of these rebounding particles is too small, it explains that the volume occupied by the positive center is also very small. If the space occupied would have been big enough, then the number of alpha particles bouncing back would also be greater. So let's say there are gold particles in the foil. He found that most of the rays pass straight through the atoms. A few rays change their path and get deflected. Lastly, very few particles bounce back. These results compelled Rutherford to come up with a new nuclear model. Let's have a look at the hypothesis put forward by him. Firstly, there's a positively charged center in an atom called nucleus. Nearly all the mass of an atom resides in the nucleus. Secondly, the electrons revolve around the nucleus in circular paths. Thirdly, the size of the nucleus is very small compared to the size of an atom. However, theoretically, there were many flaws in the hypothesis. Let's have a look at the drawbacks in Rutherford's hypothesis in the next video. Also, we will have a look at the explanation of atomic structure by another scientist named Niels Bohr in the next video.
So Rutherford's experiment shown here, which will clear your idea, and the drawbacks are modified by the Niels Bohr. So Niels Bohr has given this new model. It is called planetary model, like a planet, a sun, around the sun, earth, and all planets are moving. Like this model is suggested. He suggested that electrons moves in orbit around the nucleus. The orbit have a specific size and energy. Each orbit is having specific size and specific energy. The energy is related to its size. How the size is bigger, energy also less. It will goes on decreasing. The energy between these protons and electrons, which will bind together here to them. Okay, to nucleus and electrons are binded with the energy. So this energy is have a specific size and energy. Okay, energy is related to its size, and lowest energy is found in the smallest orbit. This orbit having a different energy. Electrons can move between each shell when gaining or losing the energy. When electron will move from one shell to another shell, that will be gain the energy or lose the energy. And it is shown by this model. The lines called energy shell, and the electrons are shown in blue dots, and this is the nucleus. Okay. To clear you Niels Bohr's in detail, which was invented in the year 1930, we will see the next clip of this small movie. I'll show you.
Rutherford's atomic model was quite commendable when it came to explaining the structure of atoms. However, it was not very appropriate theoretically. And why are we saying so? We know that any charged object which revolves in a circular motion gains acceleration gradually. Similarly, if the electron is moving fast in a circular path, then it will also gain acceleration. And on gaining acceleration, it's bound to liberate energy in some form. Now, if it continuously keeps radiating energy, then ultimately all the energy of the electron will get over and it will fall into the nucleus. This would result in high instability of the atom. But wait a second, all these things do not happen in an atom. And how do we know this? Because in nature, all the atoms are stable. That means the hypothesis put forth by Rutherford was also incorrect? Not really. The hypothesis just needed slight modifications. These were made by the next legendary scientist in our list called Niels Bohr. He made a few additional explanations to describe the atomic structure. The postulates put forward by Niels Bohr were as follows. Firstly, only certain special orbits called discrete orbits of electrons are allowed inside the atom. Secondly, while revolving in these discrete orbits, the electrons do not radiate energy. Now these points definitely tell us why an atom is so stable. But what exactly are these paths or orbits in which the electrons revolve around the nucleus? Let's understand with an example. Do you know how our solar system is? Yes, it appears somewhat like this. Now here, the sun is stationary at the center while the planets revolve around it. But have you noticed that the planets always revolve in fixed paths? We never find any planet jumping to a different path all of a sudden, right? They always encircle the sun in defined paths. In a similar way, we have the atomic structure. The nucleus acts like the sun located at the center, and the electrons are like planets which revolve in fixed, defined orbitals. These electron orbitals are referred to as shells or energy levels. Now the name energy levels gets us to an important concept. Niels Bohr suggested that the electrons revolving in these orbitals do not radiate energy. Now this is justified when we use the term energy levels, because it indicates that each shell has got a defined energy level. That means when the electrons revolve in these shells, they do not liberate any form of energy. And how do we name these shells to indicate their position? It's simple. Beginning from the one near the nucleus, we name them as the K shell, L shell, M shell, N shell, and so on. Yes, K, L, M, N, and so on. And what if we want to number them? In that case, we use the letter N in lowercase and write them as N equals 1, N equals 2, N equals 3, and so on, beginning from the one next to the nucleus. So we can name them alphabetically, or we can even number them. With all these theories and points known, do we now know the structure of a typical atom completely? The nucleus contains positive protons and the electrons revolving around in fixed orbitals. Is that how an atom is structured? Not really. We still have one more subatomic particle left. And what and where could it be? Let's find that out. It was around the year 1932 when a famous English physicist, Sir James Chadwick, found the third subatomic particle. He found that the particle had a mass almost equivalent to that of the proton. And what about its charge? Astonishingly, it had no charge. Yes, the particle was neutral. The particle was later named as neutron, denoted by the letter N. Thus, now we have the complete design of an atom. In the center lies the nucleus having positively charged protons and neutral neutrons, while the negatively charged electrons revolve in fixed orbitals around the nucleus. But how exactly are the electrons distributed in the respective orbitals? Is there a way to find out the maximum number of electrons that one orbital can contain? Or is it that the electrons are randomly scattered in the orbitals? Let's find out the answers to these questions in our upcoming video.
So that was defined by the Niels Bohr. After that, the next electron model, atomic model, is given by this the scientist Erwin Schrödinger in the year 1926. After a lot of research, he discovered that finally electrons move around the nucleus in a cloud, not in orbits. It's called as orbitals, which will help us to predict the area where we can find the electrons. What are the orbitals? He was suggested. After that, the closer position of the nucleus, the higher chance of to find the electrons. Means what, the electrons move closer to this nucleus. The low chance of find electric at the outer side, and high chance of find the electrons to the near to the nucleus. This is the cloud of the total electrons. He was suggested. To clear this one, after this we studied the different cells N1, N2, N3 in previous review. Up to 7 there are different cells are there, and it is defined as the quantum numbers of the electrons of atoms. In modern atomic theory, states that the motion of an electron location about its nucleus and its energy is characterized by not just a quantum number, but 4 quantum numbers are defined. This is the modern atomic theory. According to this, the 4 quantum numbers are defined. What are those 4 quantum numbers? First is the principal quantum number. After that, second is the orbital or azimuthal or subsidiary quantum number. This third is the magnetic quantum number, and fourth is the electron spin quantum number. So we'll see one by one. In the principal quantum number, it is represented by small n, as watched in video. It gives the information about the main energy levels to which the electron belongs. And the different electron cells are designated K, L, M, N, O, P. Like this, the other integer values are there. N is equal to 1, 2, 3, 4, 5 up to 7. These are the main principal quantum number, and what it represents the energy levels for the electrons and each shell. These are the atoms and the with the cells range from the 1 to 7, and larger the n, higher the energy to required. Okay. The second is the orbital or azimuthal or subsidiary quantum number represented by small l. It gives the information about the shape of the sub-energy level within the main energy. This main energy, within this main energy, this is the main energy, and suppose this is small strip. Inside this, there are suborbitals are there, and what is it shows? It gives the information about the shape of the sub-energy level within the main energy level to which an electron belongs. Its values depends on n also. That is the principal quantum number. The value of L range from 0 to n minus 1. For different electron subcells are designated in integer values. L is equal to 1, 2, 3, 4. Okay. Notations are S, P, D, F, and G. Sometimes it may be G, but it's not there. But up to D, we can study. The subsidiary quantum number L represents the sub-energy level with the main energy level, and represent L, and L is equal to 0 to n minus 1, and represented by letter S, P, D, F orbitals. See here the this cell, and inside this cell there are again subcells are there. This is the what? Orbital, second number quantum numbers. Third is the magnetic quantum number. It is represented by ML. It gives the information about the orientation or arrangement of sublevel in space to which an electron belongs. When electrons are moved, these sublevels are shown. It defines the spatial orientation of electron probability density cloud. Means how the electrons are spread in sublevel, and their density it is determined. Its value determined by value of L, and may range from -1, 0, or +1. The total of this 2L plus 1. How to find out this magnetic quantum number? By using this formula 2L plus 1. The electron spin quantum number. Fourth one is the electron spin quantum number. It gives the information about the spin of electrons. Electrons are moving around the nucleus, but simultaneously they are moving their axis also, around their axis also. Like around the sun, the earth is moving, but earth also moving itself. That similar concept here I can consider for electron spin quantum number ms. It gives about the spin of electrons about their own axis in the orbital. Energy level to which the electrons belongs, that is whether the spin is counterclockwise or clockwise. That spin may be clockwise or counterclockwise. Whatever the energy level, it will belongs. And its value is represented by the symbol is ms, that may be plus half or minus half. Here are some orbitals with the all the values for this L, means subsidiary quantum number ml, and the number of orbitals in that designated, it is represented by this table. Here see S orbital, These are the some sample values are given to you, and these are the representation of the SPDF shown to you. It will be clear after watching this video. Okay. See these properties of quantum number. Again, it is summarized with this tabular form. The symbol for the first quantum number n, principal values 1, 2, 3, integer values will be there, and role. What is the role? Determines the energy size. L is the second quantum number, that is angular momentum, subsidiary quantum number, azimuthal, and it will values 0, 1, 2 up to n minus 1. It will depend again on n. Okay. And third one is the magnetic quantum number ml, 0 plus minus 1 or plus 1, like plus L. It depends on again L. This subshell quantum number. It determines the orientation in the space. And fourth one is the what? Spin quantum number, represented by ms, plus minus, that will be in clockwise, anti-clockwise, describe the electron spin magnetic moment. Okay. This L is the subshells, and these subshells are represented like this: 0, 1, 2, 3. Okay. So after the summary of this quantum number, we'll watch a small video to clear you this idea related to this Bohr model and the quantum mechanics model, which will clear you the idea. Okay.
Model of the hydrogen atom, the one electron of hydrogen is in orbit around the nucleus at a certain distance r. So in the Bohr model, the electron is in orbit. In the quantum mechanics version of the hydrogen atom, we don't know exactly where the electron is, but we can say with high probability that the electron is in an orbital. And an orbital is the region of space where the electron is most likely to be found. So for hydrogen, imagine a sphere, so a three-dimensional volume, a sphere around the nucleus. And somewhere in that region of space, somewhere in that sphere, we're most likely to find the one electron of hydrogen. And so we have these two competing visions, right? So the Bohr model is classical mechanics, right? The electron orbits the nucleus like the planets around the sun. But quantum mechanics says we don't know exactly where that electron is. And the Bohr model turns out to be incorrect. And quantum mechanics has proven to be the best way to explain electrons in orbitals. And we can describe those electrons in orbitals using the four quantum numbers. And so let's look at the first quantum number here. So this is called the principal quantum number, and the principal quantum number is symbolized by n. So n is a positive integer, so n could be equal to 1, 2, 3, and so on. It indicates the main energy level occupied by the electron. So this tells us the main energy level, and you might hear this referred to as a shell sometimes. So we could say what kind of shell the electron is in. As n increases, the average distance of the electron from the nucleus increases, and therefore so does the energy. So for example, if this was our nucleus right here, and let's talk about n is equal to 1. So for n is equal to 1, let's say the average distance from the nucleus is right about here. Let's compare that with n is equal to 2. N is equal to 2 means a higher energy level, so on average, the electron is further away from the nucleus and has a higher energy associated with it. So that's the idea of the principal quantum number. You're thinking about energy levels or shells, and you're also thinking about average distance from the nucleus. All right, our second quantum number is called the angular momentum quantum number. So the angular momentum quantum number is symbolized by L, and L indicates the shape of the orbital. So this will tell us the shape of the orbital. Values for L are dependent on n. So the values for L go from 0 all the way up to n minus 1. So it could be 0, 1, 2, or however values there are up to n minus 1. For example, let's talk about the first main energy level, or the first shell. So n is equal to 1. There's only one possible value you could get for the angular momentum quantum number L. n minus 1 is equal to 0. So that's the only possible value, the only allowed value of L. When L is equal to 0, we call this an s orbital. So this is referring to an s orbital. And the shape of an s orbital is a sphere. So we've already talked about that with the hydrogen atom. So just imagine this as being a sphere, right? So a three-dimensional volume here. So the angular momentum quantum number L, since L is equal to 0, that corresponds to an s orbital. So we know that we're talking about an s orbital here, which is shaped like a sphere. So the electron is most likely to be found somewhere in that sphere. Let's do the next shell. So n is equal to 2. So if n is equal to 2, what are the allowed values for L? So L goes 0, 1, and so on, all the way up to n minus 1. So L is equal to 0, and then n minus 1 would be equal to 1. So we have two possible values for L. L could be equal to 0, and L could be equal to 1. Notice that the number of allowed values for L, right, is equal to n. So, for example, if n is equal to 1, we have 1 allowed value. If n is equal to 2, we have 2 allowed values. All right, we've already talked about what L is equal to 0, what that means, right? So L is equal to 0 means an s orbital shaped like a sphere. But now, in the second main energy level, right, or the second shell, we have another value for L. So L is equal to 1. And when L is equal to 1, we're talking about a p orbital. So L is equal to 1 means a p orbital. And the shape of a p orbital is a little bit strange, so I'll attempt to sketch it in here. So you might hear several different terms for this. So imagine this is a volume, right? So this is a three-dimensional region in here. So you could call these dumbbell-shaped or bow tie, whatever makes the most sense to you. But this is the orbital. This is the region of space where the electron is most likely to be found if it's found in a p orbital here. Sometimes you'll hear these called subshells, right? So if n is equal to 2, if we call this a shell, right? If we call this a shell, then we would call these subshells. Right, so these are subshells here, and again we're talking about orbitals. L is equal to 0 is an s orbital, L is equal to 1 is a p orbital. Let's look at the next quantum number. So let's get some more space down here. So this is the magnetic quantum number, symbolized by m sub L here. So m sub L indicates the orientation of an orbital around the nucleus. So this tells us the orientation of that orbital. And the values for ml depend on L. So ml is equal to any integral value that goes from negative L to positive L. All right, so that sounds a little bit confusing. Let's go ahead and do the example of L is equal to 0. All right, so L is equal to 0 up here. So let's go ahead and write that down here. If L is equal to 0, what are the allowed values for ml? There's only one, right? There's only one. The only possible value we could have here is 0. So when L is equal to 0, let me use a different color here. So if L is equal to 0, we know we're talking about an s orbital, right? When L is equal to 0, we're talking about an s orbital, which is shaped like a sphere. And if you think about that, we have only one allowed value for the magnetic quantum number. That tells us the orientation. So there's only one orientation for that orbital around the nucleus. And that makes sense because a sphere has only one possible orientation. So if you think about this as being an XYZ axis, excuse me, and if this is a sphere, there's only one way to orient that sphere in space. And so that's the idea of the magnetic quantum number. All right, let's do the same thing for L is equal to 1. All right, so let's look at that now. So if we're considering L is equal to 1, let me use a different color here. So L is equal to 1. Let's write that down here. If L is equal to 1, what are the allowed values for the magnetic quantum number? So ML is equal to, this goes from negative L to positive L. So any integral value from negative L to positive L. Well, negative L would be negative 1. So let's go ahead and write this in here. So we can have negative 1, 0, and positive 1. So we have 3 possible values, right? So when L is equal to 1, we have 3 possible values for the magnetic quantum number. So 1, 2, and 3. The magnetic quantum number tells us the orientations, right? So the possible orientations of the orbital or orbitals around the nucleus here. So we have 3 values for the magnetic quantum number. That means we get 3 different orientations. And we already said that when L is equal to 1, we're talking about a p orbital, and a p orbital is shaped like a dumbbell here. So we have 3 possible orientations for a dumbbell shape. Right, so if we went ahead and put some mark these axes here, let's just say this is x-axis, y-axis, and the z-axis here. So we could put a dumbbell. On the x-axis like that. So again, imagine this as being a volume. This would be a p orbital. We'd call this a px orbital, right? It's a p orbital, and it's on the x-axis here. We have 2 more orientations, right? So we could put, again, if this is x, this is y, and this is z, we could put a dumbbell, right? We could put a dumbbell here on the y-axis. So there's our second possible orientation. And then finally, if this is x, this is y, and this is z, of course we could put a dumbbell on the z-axis, like that. So this would be a pz orbital. So we could write a pz orbital here, and then this one right here would be a py orbital. So we have 3 orbitals. We have 3 p orbitals here. All right, so 1 for each axis. All right, let's go to the last quantum number. So the last quantum number is the spin quantum number. So the spin quantum number is m sub s here. And so when it says spin, I'm going to put this in quotations. Like this seems to imply that an electron is spinning on an axis. So that's not really what's happening, but let me just go ahead and draw that in here. So I could have an electron. Let me draw two different versions here. So I could have an electron spin like a top, if you will, this way, or I could have an electron spin around that axis going this way. And again, this is not actually what's happening in reality. The electrons don't really spin on an axis like a top, but it does help me to think about the fact that we have 2 possible values for the spin quantum number. So you could spin one way, so we could say the spin quantum number is equal to positive 1/2. So usually you hear that called spin up. So spin up, and we'll symbolize this with an arrow going up in later videos here. And then the other possible value for the spin quantum number, so the spin quantum number is equal to negative 1/2. So you usually hear that referred to as spin down, and you could put an arrow going down. So again, electrons aren't really spinning in a physical sense like this, but again, if you think about 2 possible ways for an electron to spin, then you get these two possible spin quantum numbers. So positive 1/2 or negative 1/2. So those are the 4 quantum numbers, and we're going to use those to again think about electrons in orbitals.
So this was the detail of this quantum number. And it was represented here. The quantum number with the spins are shown. I was not explained previously. This is for P. Similarly for this D, the third subcell. For L is equal to 3, and when L is equal to 4, these are the orbitals. For the third magnetic quantum number representation for this F, these are the shown here. Okay, so after this watching, you are clear this